This video is brought to you by mywayteaching.com.
In this part, let us study escape speed. See, if a stone is thrown by hand, again it falls back to the earth. Of course, using machines, we can shoot an object with much greater speeds, and with greater and greater initial speed, the object scales higher and higher heights. A natural query that arises in our mind is, can we throw an object with such a high initial speed that it does not fall back to the earth? Yes, it is possible. The principle of conservation of energy helps us to answer this question. Suppose the object did reach infinity and that its speed there was v(f). Object has reached infinity, there its speed is vf. The energy of an object is sum of potential and kinetic energy. As before, W1 denotes the gravitational potential energy of the object at infinity. The W1, it denotes the gravitational potential energy. The total energy of the projectile at infinity is given by, that is, E infinity is equal to W1 gravitational potential energy mvf square by 2. If the object was thrown initially with a speed that is given by vi, okay, initial speed of the object is if we consider that is equal to vi from a point which is at a distance h plus re from the center of the earth, we know re is radius of the earth, then its energy initially, that is given by E of h plus re, is equal to half mvi square. It is, and it is the sum of kinetic and potential energy gmme h plus re plus w1. By the principle of conservation of energy, this equation 1 and 2 must be equal. So in both the cases, W1 cancels, and we'll get the equation, that is mvi square by 2 minus gmme by h plus re is equal to mvf square by 2, isn't it? If RHS is a positive quantity with the minimum value 0, so must be the LHS. Thus, an object can reach infinity as long as Vi is such that mvi square by 2 minus gmme by h plus re is greater than or equal to 0. The minimum value of that initial speed corresponds to the case when LHS of this equation 3 equal to 0. That will be the minimum value of Vi. Thus, the minimum speed required for an object to reach infinity, which means escape from the earth. If you throw that object, it will never come back towards the earth. Okay, that is what it is called as escape speed. So that minimum speed is given by 1 by 2 m vi square minimum is equal to g m m e by h plus re. Okay, let it be equation number 3. If the object is thrown from the surface of the earth, in that particular case h will become 0, isn't it? So we can write that minimum initial speed to escape from the surface of the earth is equal to, it is given by vi minimum, and that is equal to square root of 2 gme divided by re. So using the relation, that is acceleration due to gravity, we know the equation which is given by gme by re square. In that particular case, we get the value of initial speed is equal to square root of 2 g re, isn't it? If you substitute the value of g, again we'll get back this equation. So this equation number 5, we can say this is equation number 4. So this equation 5, it applies equally well to an object thrown from the surface of the moon with the g, which is replaced by the acceleration due to moon's gravity on its surface, and re is replaced with the radius of the moon. So both are smaller than their values on earth, and escape speed for the moon, it is 2.3 kilometer per second, escape speed for moon. This is about 5 times smaller, which is when we compare it with the escape speed of earth. This is the reason that moon has no atmosphere. Gas molecules, if formed on the surface of the moon having velocities larger than this, they will escape the gravitational pull of the moon. So there is no, what we can say, chance for the atmosphere in the surface of the moon, because the velocity of that molecules can be greater than 2.3 kilometer per second, so it will escape that gravitational pull in the surface of the moon. Okay, now let us see a very simple problem. Two uniform solid spheres of equal radii r but mass m and 4m have a center uh, to center separation, that is 6r. As shown in the figure, the two spheres are held fixed. A projectile of mass m is projected from the surface of the sphere of mass m directly towards the center of the second sphere. So obtain an expression for the minimum speed v of the projectile so that it reaches the surface of the second sphere. Okay, you just consider the figure which is given here. So two uniform solid spheres of radii r. So here are the two spheres, having one having the mass m and another one having the mass 4m. They have center to center separation, that is given by 6r. The two spheres are held fixed. A projectile of mass m, here a projectile of mass m is projected from the surface of the sphere of mass m towards the center of the second sphere. So obtain an expression for the minimum speed v of the projectile so that it reaches the surface of the second sphere. The projectile is acted upon by two mutually opposing gravitational forces of the two spheres. Even this is having that gravitational force, and even this sphere. So the neutral point n is defined as the position where the two forces cancel. So this point n is the neutral point. Okay, where the two forces cancel each other. So here we are considering that is on, that is equal to r. So in that case we can write gmm by r square is equal to 4 gmm by 6r minus r the whole square. The gravitational force due to this first one, the mass m and the small mass m, and the distance between this neutral point and this O is r. In the second case, the mass is 4m, so 4 gm and this mass m, and the distance between this neutral point and this c is given by 6r minus r. So we can cancel these things. We can write 6r minus r the whole square is equal to 4r square, isn't it? So if you take the square root, we'll get the value that is plus or minus 2r. So r is equal to 2r, or it can be minus 6r. If you consider this equation, once you just consider plus 2r, once minus 2r. If you consider plus 2r, in that case it will be 2r. If you consider minus 2r, in that case it will be minus 6r. Okay. So the neutral point r is equal to minus 6r does not concern. So here we are neglecting this one and we are taking only r is equal to 2r. It is sufficient to project the particle with a speed which would enable it to reach n. Thereafter, the greater gravitational pull of 4m would suffice. The mechanical energy at the surface of m is given by the mechanical energy at the surface of m is given by ei is equal to 1 by 2 m v square minus gm by r minus 4 gm by 5r. So at the neutral point n, the speed approaches 0. The mechanical energy at n is purely potential. When speed approaches 0, in that case, gm m by r minus 4 gmm by 4r. So from the principle of conservation of mechanical energy, we can write 1 by 2 v square minus gm by r minus 4 gm by 5r is equal to minus gm by 2r minus gm by r. So if you simplify this, we get v square is equal to 2gm by r, that is 4 by 5 minus 1 by 2. So v is equal to 3gm by 5r whole raised to 1 by 2. Okay.